reactivity. In chemistry, mainly inorganic and organic, we have two types of questions distinctly. One is theoretical questions. The other one are reactions. What do you mean by theoretical questions? For instance, in our earlier classes, we have discussed SO2. So many things about SO2 we discussed. To start with, the oxidation state sulfur plus 4 and the structure double bond O, double bond O. It has 2 sigma bonds and 2 pi bonds, and sulfur has a lone pair, 2 bond pair and 1 lone pair, therefore it has a bent structure. The geometry, the sigma bonds, the pi bonds, lone pair, oxidation state, and one of the pi bonds is indeed a d pi p pi bond, a pi bond in which d orbital of sulfur is involved. And since you have a lone pair, wherever there is a lone pair, the molecule is said to be polar, except of course XeF2 and XeFO. If you have a lone pair, the molecule is said to be polar. So these are all theoretical aspects. And one more, this sulfur dioxide is diamagnetic. How can we know? You know, the total number of electrons is odd number, diamagnetic. So we discussed the structure, the shape, the hybridization, whether it is polar or not, the number of d pi p pi bonds, and the hybridization 6 plus 0 by 2, which is 3 sp2. So the formula for hybridization, the rule for polarity, the number of d pi p pi bonds, the number of lone pairs, the structure, the oxidation state, the magnetic nature. And you also know that sulfur dioxide is an acidic oxide. How can you know that? Acidic. Acidic because it is a non-metal oxide. And it's an anhydride of H2SO3. When you remove water from an acid called sulfurous acid, you get SO2. These are mostly the theoretical aspects. It's all good. But how does SO2 react with K2Cr2O7? The big question. In fact, many of you might even think that inorganic means reactions, or rather chemistry means reactions, how a substance reacts with the other. And you are not wrong when you consider things like that. So we indeed spent a lot of time in theoretical aspects, but only these theoretical aspects only will decide the reactivity. So we have to learn reactions not in isolation, not one reaction after the other, which will become our task very difficult, very difficult. Like there are so many reactions, how can we remember all those things? We can only know the mentality of an element, mentality of a compound, why compounds and elements react the way they do. So SO2, you have sulfur in its plus 4 oxidation state, and you already know there is a lone pair which will cause repulsion to the bond pairs. Therefore, the mentality of SO2 is more to use those 2 electrons also. So we study the reacting mentality, which is called reactivity, and that's how only we go about the task of reactions of organic and inorganic basically. Right. So I discuss the reactivity now. This will definitely include so many things which we have already learned. See, I roughly will teach you 20 points to summarize most of the reactions. First point, this is less stable given a chance. What do you mean by given a chance? Given a chance. Less stable given a chance, that is slight heating. Given a chance, that is slight heating, Because I insist on this point, slight heating, because when you heat very strongly, you don't know what might happen. Anything may happen. So it should be a natural process. When you're heating slightly, something takes place in a natural way. Wants to become more stable. Wants to become more stable. Less stable, given a chance, wants to become more stable. So, this is the basic idea of all reactions. Anything happens for betterment only. If somebody does something, he definitely does that for his betterment. So, atoms and molecules, ions, they also behave in that direction only. First point, all nitrogen atoms, in fact, it would have been enough if I have simply written nitrogen in brackets, but my emphasis is on atom. All nitrogen atoms want to become N2, the nitrogen molecule. You might ask me why? Because the N2 molecule contains a triple bond and it's a very strong bond. So, the reason the triple bond is very strong, and you can say nitrogen is almost an inert gas, it doesn't react. Evidence, what is the evidence for what I am saying? You have 79% roughly nitrogen in air and roughly 20% oxygen. If nitrogen starts reacting with oxygen, what would have happened? All the nitrogen and oxygen would have combined to give nitric oxide. We wouldn't have got a single molecule of oxygen for breathing, If nitrogen starts reacting with oxygen, all oxygen would have been consumed by nitrogen itself, and the environment must have been full of N2 and nitric oxide rather than oxygen. But this reaction takes place only at a temperature of 3000 degrees centigrade or 3000 volts, a high temperature, 3000 volts, very high voltage. Only when lightnings occur, nitrogen combines with oxygen, only with the help of high voltage produced by lightnings. It happens only in the upper environment. I sincerely believe you won't find a single molecule of NO in this room. The reason, you have nitrogen, you have oxygen, but you don't have that kind of voltage for them to combine. So, all nitrogens want to become N2, reason being N triple bond N being very, very strong, can't be broken easily. Remember, nitrogen can be said to be a less reactive gas. I can't say a non-reactive gas, but definitely it is a less reactive gas, more or less a noble gas. It's like noble gases, helium, neon, which do not easily combine. Nitrogen also doesn't combine easily. And second point, all oxygen atoms want to become H2O. Once again, what is the reason? Here the OH bond is the second strongest bond, of course, covalent bond. We can never compare the strengths of ionic bonds, which are electrostatic attractions, which depend on so many factors. So, the less said about the stability of ionic compounds, the better. So we focus on second strongest almost covalent bond. I may be overgeneralizing, but that is enough for you at your level. Like FH bond is the strongest bond. HF bond is the strongest bond, strongest covalent bond. This is the second strongest bond. In fact, you might have remembered O bond is the second weakest bond when it comes to reactivity. O bond is the second weakest bond because of the presence of too many lone pairs. You have too many lone pairs there. And FF bond by the same yardstick is the strongest bond. FF. This is strongest bond and this is the weakest bond. Because of 3 lone pairs here and 2 lone pairs, 2 to 4 lone pairs, too much of repulsion. So, OH bond is very strong, and when you heat water also, at best it vaporizes. You get H2O in gaseous state, but definitely it's not very easy to get hydrogen and oxygen atoms out of that. The molecules as such may vaporize, go to gaseous state, but still remain H2O. The bonds are not broken. However, high heating you do 400, 500, even 600 degrees also, water doesn't break. I mean, the bonds in water do not break. That's the reason 75% of earth is covered with water. If water decides not to be stable, what would have happened? All water would have broken into hydrogen and oxygen molecules, and we wouldn't have got a single molecule of water to drink. So thank God for that. N2 is highly stable, it doesn't want to react with oxygen. That's why we get oxygen for breathing. H2O is very stable, that's why we get water for life. Right. All oxygen atoms want to become H2O. And in our earlier classes, we have seen a host of molecules which contain a weak bond, H2O2, the oxygen-oxygen single bond. Once again, you have a peroxy bond which is weak. H2O2 wants to become H2O. Why? The same reason. H2O is highly stable and oxygen-oxygen single bond is very, very, very weak, peroxy bond. That's why we indeed looked at substances containing that peroxy linkage. We were particular about finding whether a molecule has a peroxy bond or not. Now, even ozone wants to become O2. Ozone, you in fact have a coordinated bond, and of course that resonates. It's not always a double bond, it's not always a single bond. The double bond will shift there and the A2 bond will be shifting. So it's like a 1.51, 1.5 bond. So once again, oxygen-oxygen single bond is also once again weak. Therefore, ozone wants to become O2. Wants to become, this is the important word here. They want to become. They do anything with the intention of getting themselves converted into. So nobody is forcing them to become, nobody is forcing H2O2 to become H2O. It itself wants to become H2O, wants to become H2O, and it gladly gives you oxygen, you know. If you want, it can gladly give you an oxygen atom. A substance that can give an oxygen atom, who could that be? An oxidizing agent. Who else? H2O2 happily gives you an oxygen, doesn't object. You need not even ask H2O2, it just gives oxygen, that's why. Next, CaOCl2, the so-called bleaching powder, wants to become CaCl2. Look here, it once again contains that weak bond OCl. 2 lone pairs, 3 lone pairs. So, all these substances, if you observe what is common with all these, they all have an extra oxygen, unnecessary oxygen atom that is causing some kind of trouble. Had this oxygen not been there, calcium chloride would have been a perfectly ionic molecule, and perhaps the bonds would have been electrostatic strong. Because of the presence of this extra oxygen, the molecule is facing some trouble. And once again, NaHClO, hypochlorous acid, that also contains OCl bond, same trouble, wants to become HCl. NaClO in a natural way wants to become NaCl. When you heat it strongly, perhaps you may get NaClO3 or anything else. I never talk about those reactions which involve a lot of heat, because all those reactions are catalyzed by heat. They are because of heat, and they are because of some kind of external force you are using. So how can anyone predict what happens when you use a lot of force? That is unpredictable. So we are predicting reactions where the process, or where the progression is natural. Never ask me about unnatural reactions. I am not a case for that. Perhaps you may have to memorize. That's why people will tell you you have to memorize a lot in chemistry. That is not true. 75% of the reactions can be predicted in a natural manner. Of course, there are maybe 50, 60 reactions where a lot of heat is involved and where the products are quite unpredictable. Suppose if I take a big glass object and throw that from a 7-story building, what will happen to that? Who knows? It may break into 100 pieces, 1000 pieces. So never go after such reactions. It's like going after mirages in a desert. For example, H3PO3 heating to 450 degrees. What will happen? How can I know? Anything can happen. 450 degrees, it's no less temperature. At this temperature, anything will happen, but thankfully, I think our NCERT has mentioned all the oxy acids of phosphorus in their intermediate oxidation state. Here, phosphorus is in +3 state, +3, whereas phosphorus can go as low as -3 and as high as +5. Here it is in +3 state. So, NCERT, it is mentioned that whenever there is an oxy acid of phosphorus in intermediate oxidation state, it will go to the least pH 3 and to the highest H3PO4. Okay, that statement perhaps will help remember a few reactions, but they are, I don't think they are of great significance. No doubt the statement is good, no doubt statement is valid, but that you can't generalize all such reactions. It is only with phosphorus once again. I can't say the same with nitrogen. Suppose there is a molecule of nitrogen in intermediate oxidation state, I cannot predict its reactivity. Now, PbO2 wants to become PbO. You must have seen why. Why? If you remember, it is inert pair effect at work, +4 +2, +4 +2, because lead doesn't prefer a higher oxidation state, also wants to become, so this is inert pair effect. Then all peroxy substances want to become oxy. All peroxy substances want to become oxy substances. What is a peroxy substance? A substance which is containing the weak oxygen single bond. So, what is common among all these? H2O2, O3, CaO, Cl2, HCl, NaCl, PbO2. These are all less stable due to extra oxygen. Less stable due to extra, I would rather say an unnecessary oxygen, and these are obviously more stable. So, any reaction involving H2O2, it is not very difficult for us to predict one of the products, it is H2O all the way. If you find H2O2 on the left side, most cases you see H2O on the right side. Right. So, what do you mean by less stable, more stable? How can you decide on stability? Very simple. Among these compounds H2O2, H2O, O3, O2, which are the ones you have learnt in your earliest classes? Did you study H2O2 in your class 6 or class 7, or H2O you studied in 6th or 7th or 8th, class 6, class 7, class 8? So, you have studied these only. Why are you taught these molecules at a very early age in your life? Because they are everywhere around you. Who doesn't know water? Who doesn't know sodium chloride, the salt? We all know these molecules, and because they are present everywhere in the world around us. Why are they present everywhere? Because they are more stable. The more stable. H2O2 is not stable. You can't see that everywhere. Even if you keep a bottle of H2O2, no guarantee it will remain H2O2 after 10 days. A bottle of H2O2 will automatically become H2O. So, and we are worried about the depletion of ozone layer, ozone getting converted to O2. Therefore, these are all molecules which are stable. Therefore, the compounds you study in your earlier classes are more stable, and you can generalize that way. Whatever you study in class 8, 9, 10, they are definitely more stable than what you study in 11th, 12th and further on. And beyond your JEE level chemistry, you might even be talking about very, very, very unstable compounds, intermediates, reaction intermediates, which do not live longer. They don't have a long life because they are further unstable, further less stable. Therefore, this is the reactivity of these substances. We will apply all these principles. I wouldn't say these are principles, at least some insight into reactivity. And there definitely can be some variations. Let's not bother about the variations. Right. A second set of ions. Ferrous wants to become ferric ion. Ferrous ion wants to become ferric. Why? It's easy to understand. Because it has a 3d6 configuration, and By losing one more electron, it becomes 3d5 half filled. It gets that half filled configuration. Therefore, ferrous wants to become ferric in a natural way. So, how can ferrous become ferric? By losing one more electron. If you remember, one who gives electrons is called a reducing agent. Therefore, any question, if you see ferrous on the left side, you can easily imagine ferric is going to be on the other side. Suppose there is a reaction between a solution of ferrous sulfate and a solution of permanganate. You might even say, of course, with the help of acid, you can definitely get ferric as one of the products. Sir, how are you so sure? Yeah, ferrous wants to lose electrons and permanganate is somebody who can gain electrons. I will tell you why permanganate gains electrons a little later. Okay, so we will discuss these examples which might suit 75% of the reactions, and it's enough for you to learn 75% reactions hardly in 1.5 hours. At best, I will teach this reactivity for an hour and a half. So, if you can learn 75% of reactions in hour and a half, for which you might otherwise need to spend more than 100 hours, you should be at least be convinced with that. Don't ask me about the remaining 25%, where there is no, cannot be predicted. They are condition forced. They are forced because of high temperature pressures. By using high temperature pressure, anything can happen. So, I definitely cannot predict reactions where there is no what you call generalization. Now, ferrous wants to become ferric. Sn2 plus wants to become Sn4 plus. Once again, another reducing agent. Why? Here is the case, inert pair effect. No, it has no inert pair effect and wants to get rid of lone pair. Wants to get rid of lone pair. It's not just tandem. Perhaps all non-metals want to use as many electrons as possible. For example, SnCl2 is not happy the way it is. Why? There is a lone pair bothering. Therefore, it wants to use those 2 electrons also. It's not just with tandem. Of course, tandem is a metal, but it has got some non-metallic properties also. So, all non-metals, they want to use as many electrons as possible to get rid of those unused pairs of electrons which might otherwise disturb the structure. Sn2 plus wants to become Sn4 plus. Next, Pb4 plus we already mentioned wants to become Pb2 plus. Here you have got the case of inert pair effect. You might ask me, sir, is lead not afraid of lone pair? Because in Pb2 there might be a lone pair. Lead is definitely not afraid of that. Lead being a very big atom, it's not bothered about lone pairs. Now, oxalate wants to become carbon dioxide. It once again contains weak bonds by losing 2 electrons. One oxalate loses 2 carbon dioxides. One oxalate gives 2 electrons. Once again a reducing agent, a reducing agent, a reducing agent. These are all giving electrons. And there is something surprising. Copper plus wants to become copper 2 plus. Despite D10, copper plus has a stable D10 configuration. Despite D10, it wants to become copper 2 plus. Isn't it surprising? A D10, a completely filled orbit wants to become D9. Definitely it is surprising, but there are other reasons than this just electronic configuration. Here, small ions are more hydrated. Copper 2 is smaller than copper 1. This is smaller than this one, and this gets more hydration energy. Small ions are more hydrated. So, if you remember, these are all principles we studied in the theoretical aspect only. We discussed the existence of lone pairs. We discussed the existence of stable configurations. So, all the theoretical points we have taught, they are reflected in reactivity. What else reflects? So, why ferrous behaves the way it do? Because of its theory only. Somebody told him, you get D5, you would be stable, you would be happy. Therefore, the theoretical aspects are also equally important. The hybridization, the lone pairs, the presence of lone pair, which will cause repulsion to the geometry. So, that is why we are able to generalize that non-metals want to use as many bonds as formed. They want to form as many bonds as possible. to get rid of lone pair. That's another generalization which will help us to understand many reactions. So, copper plus wants to become copper 2 plus. We discussed hydration energy earlier, and we discussed small ions are more hydrated. Therefore, this is one thing. Maybe this is point number 3. Pi bond wants to become sigma bond. Why? Why do you think so? Pi bond wants to become sigma bond. Very easy to understand. A weak bond. Pi bond is a weak bond. No need to say sigma bond is a stronger one. Strong. So, all reactions where pi bond is involved, the pi bond wants to break to become a sigma bond. Once again, a natural progression. Now, 4. Non-metals want to form as many bonds as possible. Why? To get rid of lone pairs. Look here, I am once again telling you, I am not teaching a small classroom. I am addressing a huge audience elsewhere outside. I am live on the video. I know that. I shouldn't give careless statements. You might be ready to show me dozens of counter examples, sir. It doesn't happen like this here. But it's not a disclaimer definitely, but I am telling you, I am here to help 75% of the reactions only. I never tell you that I can predict I can give you a method or I can give you a magic wand where you can predict all the 100% reactions. That definitely is not the purpose of this lecture. Don't mistake me. I want to help. If you are a master of chemistry, okay, it may not have, if you already know all the reactions, this definitely does not help in any way. If you already know the reactions, where is the need for all these principles? It's only for those who are still struggling to get an insight into reactivity. I am presenting my humble insight into it. These are not rules, these are not what you call strong generalizations, they don't have strong foundation, and definitely they are not memory techniques. They have a reason also, but sometimes something else may outsmart the reason also. Some compounds behave irrationally because of the circumstances, but in a natural way no one can question these things. So, don't try to send me counter examples for this. Definitely this is not a disclaimer I am telling you. I am not disclaiming anything here. I am claiming as much as students require. The present examination need and to have an insight into majority of reactions in quick time. I am attempting only an hour and a half here, and don't expect me to teach everything in this hour and a half. Neither you have the time nor have the patience. I know that. Now, 5. Non-metals want to form as many bonds as possible to get rid of lone pairs. Compounds in maximum oxidation state we discussed the oxidation states, and I told you the maximum oxidation state is equal to group number. Compounds in maximum oxidation state can act as oxidizing agents only. At the back of your mind, you should always have this. Without this, perhaps reducing agent behind every natural reaction, you should have this. Reducing agent is one who gives electrons. I discussed this earlier, but you have this behind the back of your mind. Every reaction, one who gives electrons. Compounds in maximum oxidation state can act as oxidizing agents only. Listen to me. I never said they act as oxidizing agents. If they want, they can act as oxidizing agents only. They have no choice but to behave as oxidizing agents. Okay, what does it mean? They cannot act as reducing agents. What's the meaning of this? They cannot act as reducing agents. Listen. So, why? It's very sensible, very easy to understand. Look here. You have a manganese atom here whose electronic configuration is argon 3d5 4s2. Listen. Suppose you want to gain one electron from manganese. Okay, it will give, it's a metal. Metals are reducing agents. Metals are reducing agents. Metals lose electrons easily. Not all metals, you know that copper, silver, gold, they don't lose electrons. They don't want to lose electrons. We discussed that point in metallurgy. So you have to combine all those things. Okay, so metals lose electrons easily. They are good reducing agents. One who gives electrons is called a reducing agent. Metals lose electrons easily. They are reducing agents. Listen to me. So, manganese can give 1 electron, 2 electrons, the 2 electrons in the outermost shell. All metals would perhaps lose electrons from the outermost shell only, but it's not the case with the transition metals. They treat these electrons also as valence electrons. For them, D5 and S2 both are like one and the same. Both are valence electrons. Therefore, manganese, if you want ask manganese, will you please give me 1 electron? Yes, it gives plus. One more, okay, plus 2. But manganese can use these 5 electrons also. We have discussed this in transition metals. We said that not only Ns electrons but N-1d also participate in bonding. So, manganese 1 more electron please, okay, plus 3, plus 4, plus 5, plus 6, plus 7. Manganese is ready to lose 7 electrons, and that's why that happens to be its maximum oxidation state. You know, manganese belongs to 7th group, 7b, and minimum is 0, maximum is plus 7. Therefore, manganese is ready to lose 7 electrons, as high as 7 electrons. And if you ask 1 more electron, manganese would rather be angry. Idiot, I have given you 7 electrons, you still want me 1 more electron. And you are asking from that argon. So, manganese cannot give more than 7 electrons. I am not telling you that manganese will start taking electrons now. I am only telling you manganese cannot give any more. It has given whatever it has. It has given all the money it has, and how can you expect it to give more? So, when you are in the maximum oxidation state, you can act as oxidizing agent only. Look here. Suppose here is a 7-storied building, 1, 2, 3, 4, 5, 6, 7. And this is terrace, open to sky. Suppose I am standing for an elevator in the terrace. I am standing for a lift in the terrace. What is the question you should not ask me? Sir, which way you are going? Up or down? When I am on the terrace, do I still have 1 more floor to go up? That is open to sky. So, the question doesn't arise whether you go up or down. I am waiting for an elevator, obviously to go down only. I might even be angry if you ask, sir, which way you are going, up or down. I would rather say, I don't need an elevator to go up. It's enough if I simply jump. Therefore, when you are in the maximum oxidation state, you can take electrons if you want. There is no rule that you should take electrons. So, I have already written this. So, compounds in maximum oxidation state can act as oxidizing agents only, and of course, opposites are opposite. Minimum oxidation state, when you are in the cellar, in the groundest floor, it is the cellar. There is no question of going down, you can only go up. So, minimum oxidation state, you can go up only. How can you go up? When you are in minus 2, how can you go to 0? By losing those 2 electrons. What is minus 2? A gain of 2 electrons. From a gain of 2 electrons to 0 means losing 2 electrons. So, when you are in the minimum, you lose electrons to go up, and when you are in the maximum, you take electrons to go down. You use the opposite direction. So, But KMnO4, the potassium permanganate, K2Cr2O7, HiO4, HNO3, these four always act as oxidizing agents. Always. They are in their maximum oxidation state. They can act as oxidizing agents only. There is no rule that they should act as oxidizing agents, but they definitely act as oxidizing agents. You have to understand the meaning of this can. Emphasis is on this can. Once again, they always act as oxidizing agents. Listen, they have reached their maximum. There is no reason for them to come down. If they want, they can stay there in the maximum, they can stay there in the terrace only, but they definitely will not assert their right to stay there. They will come down if necessary. How can they come down? From +7 to +6 to +5 to +4. How? By taking electrons. And one who takes electrons is called, I won't define it that way, one who gives electrons is called a reducing agent, and opposites are opposite. I told you, one who gives electrons is a reducing agent. And HClO4, H3PO4, they are in their maximum oxidation state. They never act as oxidizing agents. Means they have reached the top and they remain at the top forever. Means it's not, you cannot bring them down easily, I repeat, in a natural way. Don't tell me, sir, I will heat H3PO4 and anything will happen. When you heat, anything can happen. Don't talk me about reactions involving high energies. So they never act as oxidizing agents. They never act as oxidizing agents. Okay, that's okay. To give it a finality, I am writing natural way. In a natural way, reactions in a natural way. I am not teaching unnatural reactions. I can only teach you normal reactions, and definitely abnormal reactions. Abnormal in the abnormal itself means they are abnormal. I am not an abnormal person. Now, HClO4, H3PO4 never act as oxidizing agents. So, reactivity, reactions which take place naturally. I think this will settle all your doubts. Sir, H3PO4 on heating will give pH3 also. Okay, on heating anything can happen. Okay. I am not discussing that aspect. H2SO4. So, these are compounds in maximum oxidation state. So, they have reached their peak, but they have reached their peak, and when you reach the peak, you can come down or you can stay there. You have two choices, stay there. Sir, I have reached the peak, what shall I do? Stay there or come down? What else can you do? You can't go further up. So, these four are the people who are always ready to come down, and these three, once they reach the top, once they reach the peak, they will remain there forever. Means you cannot bring them down. Right. The word, technical word is they are stable. They are stable. I don't want to use that word. Never acts as. H2SO4 rarely acts as oxidizing agent. Occasionally acts as oxidizing agent against cyanide, bromide, iodide. Against these three, that will act as an oxidizing agent. Cyanide, bromide, iodide, yes. H2SO4, though in its maximum oxidation. So, most of the time H2SO4 behaves like a spectator, in the sense it doesn't do anything. H2SO4 remains there itself most of the time. But with cyanide, bromide, iodide, it will come down. It will take electrons. These two will not take electrons from anyone. These two will take electrons from anyone. Okay, the question is, sometimes manganese takes 5 electrons, sometimes 3. I am not discussing the different abilities. I am just telling you the natural way. When does it accept 5? When does it accept 3? Okay, that we will discuss later. Now, H2SO4 against cyanide, of course, when cyanide heated, it will act as an oxidizing agent. Perhaps the 7th point, metals are reducing agents. This is the 7th point. Minimum oxidation state, you can act as, no need that you should act as, you can act as reducing agents only. Look here, In NH3, ammonia is in its minimum -3 state, but ammonia doesn't behave as a reducing agent. It doesn't give electrons easily. Ammonia remains ammonia. What is the nature of ammonia? We discussed more things about ammonia. Ammonia, its main worry is to get rid of the lone pair. Ammonia is worried about losing the lone pair. So, don't tell me, sir, ammonia is in minimum state, therefore it will act as a reducing agent. I never said that when you are in minimum, you act as a reducing agent. I only tell you that you can act as reducing agent only. Means you cannot act as oxidizing. If you understand this statement, perhaps you can answer 25% of the reactions very easily. I am not saying you should act as reducing agent. There is no compulsion. When you are in the minimum, stay there or come up. I am only telling you, you don't have a lower floor than that. When you reach the cellar of a building, cellar, the parking area, and you can't go down. That's what I am saying. That is the least possible place. I mean, groundest floor. Now, reducing agents only. 8. Minimum oxidation state, you can act as reducing agents only. Okay, let me discuss a few reducing agents. Like H2S is definitely a reducing agent. H2S. HI is a very popular reducing agent. Hydrogen iodide. Iodine is in -1 state. It will definitely act as reducing agent. But I can't guarantee the same with HF. HF will never act as reducing agent. HF, you have an F minus. F minus will never give electrons. F minus is humanly impossible to make F minus to F2. 2F minus to F2 is impossible. And a person who indeed did that was given a Nobel Prize, Moisen in 1906 perhaps. He uses so much of so many special conditions to actually manufacture fluorine. Manufacturing fluorine is an uphill task. Therefore, I never tell you when you are in the minimum, you are forced to lose electrons. I definitely will not say that. You can only act as a reducing agent. H2S, HI, there are some other, even phosphine PH3 definitely can act as a reducing agent, PH3. Now, all reactions of H2S, when I say all, 99% of the reactions, don't show me one or two counter examples. All reactions of H2S, you get a yellow-white precipitate, yellow-white. Sometimes with less intensity it appears white also. When you have a huge precipitate, it is yellow-white. Turbidity, you can say, is a precipitate, yellow-white turbidity. You justify this, H2S minimum. So, H2S is in its minimum oxidation state, H2S -2. It wants to go up. Indeed, sulfur wants to use all the electrons, +8. Sulfur would have been happy to +6. Sulfur would have been happy to use all the electrons from -2 to +6. But what happens is, when H2S is converted to sulfur, it precipitates in water because sulfur is not soluble in water. Sir, why are you talking about water? Mind you, in all redox reactions, we have to perform them in solution state only. In what state do you think reactions will take place? Just imagine, if you mix these two solids, what will you get? Nothing. These two solids are mixed. What will you get? Nothing. So, when will reaction, in what conditions reactions take place? A chemical reaction takes place only when molecules collide. So, where can they collide? Either in the gaseous state or in solution state, mind you. Even in liquid state also, the movement is not random. The liquid state. Solute particles, what is a solute particle? Suppose when you add glucose molecule in water, what happens? Glucose will be moving in all directions. So, solute particle is something which moves freely in a solvent. What is a gas molecule? A molecule that moves freely. What is most important? You should move freely. You should move in a zigzag manner so that you will be able to collide, and only collisions lead to chemical reaction. Therefore, this H2S must be combined with some kind of solution. Therefore, by trying to go to the plus 6 state, sulfur actually precipitates. So, you will see sulfur in most of the reactions of H2S. You roughly have 20 reactions of H2S, and I do not think there is no reaction which some other product is there. Even if it is there, I can't help that. I can only teach you what happens in a natural way. H2S, you are heating somebody with K2Cr2O7, okay, sulfur will become, even that sulfur also burns. Suppose you are heating in solid state, that sulfur will burn. That is no big deal. Anybody knows sulfur burns to give SO2 if you heat it further, SO3.